Lecture 3.4, Spectral Line Strength. The image that we've been using for this unit is a very high resolution image of the sun spectrum. It starts at red wavelengths up here and they go across, and then it continues the spectrum down and it keeps wrapping around to fit it all on one page. So this right here, I believe, is the hydrogen alpha line, the 3-to-2 transition in hydrogen. These lines are due to sodium. Calcium lines are down here. In order to measure the strengths of all of these different lines, you can see that like that H alpha line is very strong. Some of these other ones are very weak. We want a way of quantifying how strong they are. So if we imagine plotting the intensity through the line, it might look something like this. If you think about what the shaded area is right here, this is kind of the total of all of the energy that's been taken out of the spectrum due to the spectral line. So we could define the equivalent width of this line as saying, well, okay, what would the width of a rectangle be so that you took out all of the radiation in the line? So there wasn't, it didn't dip down like halfway, but it went all the way down to zero. So what's the width of this rectangle so that this area is the same as that area? That's kind of what you can imagine doing in order to quantify how strong a line is. All right, let's think about the hydrogen Balmer lines. This is a spectra of an A star. So this is the wavelength scale is in angstrom instead of nanometers. So if you just divide that by 10, you get nanometers. So 656 nanometers is right there. That's the H alpha line right here. There's the H beta line. H gamma is here. In order for these Balmer lines to appear in a star spectrum, a number of things have to be true. So first, the star must contain hydrogen, obviously. If there were no hydrogen in the star, you wouldn't see spectral lines due to hydrogen absorption. The second thing is that hydrogen must be in the proper ionization state, in other words, neutral. So if the star was so hot that all of the hydrogen were ionized, there would be no bound atoms. There would be no neutral atoms, and so you can't form spectral lines then. So it's got to be in the right ionization state. And then for an absorption line to form, it also has to be in the right excitation state. So with hydrogen, to get these Balmer lines to appear, you already had to have an electron sitting in that n equals 2 state, just kind of waiting there for a photon to come along so it could absorb the photon and get kicked up to an even higher state. So all three of these things must be true. Now, you don't have to have all of the hydrogen being in the proper excitation state. You just have to have some hydrogen in the star being in the right excitation and ionization state. Okay, so we're going to define the total number of atoms for a given element X. So n means number. Brackets just mean, okay, I'm going to say how many atoms do I have for some element X. This is now a little more specific. How many atoms do I have for element X that are in ionization state I? And now if we add an n to it, this is going to be how many atoms do I have of element X in ionization state I and in energy level N. So in the excited state N. So increasingly more and more specific details about the state of the atom. Ultimately, the line strength depends on this quantity right here. It depends on the atoms being in the right ionization state and in the right excitation state. But we're going to break this apart. So this first term is the number of atoms in the right ionization state and in the right excitation state. It's the ratio of those to just the number of atoms in the right ionization state. This middle one is just how many atoms do I have in the right ionization state compared to the total number of atoms. And this one over here is how many atoms do I have that are the right element compared to the total number of atoms in the star. This first term tells us about the excitation of the atom, which is given by the Boltzmann equation. The second term tells us about the ionization state, which will be described by the Saha equation. And the last term tells us about the abundance, or how common a particular element is in the star compared to the total. And we're going to look at each of those terms in turn. So we're going to assume local thermodynamic equilibrium for these calculations. Your book talks about this a little bit more in depth, but what we imagine is that the atmosphere of a star is a very complicated place. You have different elements flying around. Some of them, you might have some neutral helium here. There's a neutral hydrogen atom. Here's a neutral hydrogen atom, but then it's in an excited state. You might have free protons, you have free electrons. You just have this collection of all these particles with different velocities all flying around inside the atmosphere. For the atmosphere to be in local thermodynamic equilibrium, we're going to assume that the rate of ionization is balanced by recombination. So it's not getting more and more ionized over time, but there's a balance. We'll also assume that the rate of excitation is balanced by de-excitation. And, what we want to do is to be able to calculate, well, if we're in equilibrium, how many atoms, and at a certain temperature, how many atoms are in an excited state compared to the ground state? How many atoms are ionized compared to or neutral? All right, so let's look at this first term in the line strength equation. This first term is called the excitation term. So we imagine, here's kind of a idealized case where we have two energy levels. EB is going to be the upper energy state, EA is going to be the lower state. We'll call NB the number of atoms that are in this upper state. NA will be the number in the lower state. And GA and GB are the statistical weights or the degeneracies of each of these levels. So GB will be the degeneracy of that higher state. GA will be the degeneracy or the statistical weight of the lower state. We'll assume that the gas is at some temperature T, and of course we have the Boltzmann constant. And one of the results of statistical mechanics is called the Boltzmann distribution, and it tells us how many atoms will be in the upper state compared to the lower state. So the ratio of the populations of those two states is given by this term, and you can simplify it like this. So it's equal to the ratio of the statistical weights, or the degeneracies of the two states, times this exponential term that depends on the energy difference divided by kT. So it's a fairly simple expression, actually. So let's look at this in practice. Let's calculate the ratio of the number of hydrogen atoms in the first excited state to the ground state for the sun. So there's the Boltzmann distribution. We know that the degeneracy, or the statistical weight for the hydrogen levels, is just 2n squared. So we wanted to look at the ratio of the first excited state, that's the n equals 2 state. The ground state is the n equals 1 state. So the upper state, n is just equal to 2. So you get 2 times 2 squared. Ground state, n is 1. 2 times 1 squared. So we get just 4 times that. Now we want to calculate this term. So the energy level of the second excited state, you can calculate it, but it's minus 3.4. Ground state is minus 13.6 electron volts. The temperature is 5780 Kelvin, and again, this is and 1 over 11,600 is the value of K in electron volts per Kelvin. So when you plug all that in, you get minus 20.5. So this is the value that you now go back and plug in right here. So that ratio is just 4 times e to the minus 20.5. So you get that. So a very, very, very small fraction of hydrogen atoms are actually in that n equals 2 state compared to the ground state. Okay, so another way of visualizing this is, let's say that you have, for every one atom in the ground state, you'll have 5.1 times 10 to the negative ninth in the first excited state. If you go through and you plug in G3 over G1, so if you calculated the number in the second excited state, you'd find that you get 2.6 times 10 to the negative 10th. So you get even fewer up there, and then fewer. So as you go up and up and up, because that energy difference gets bigger, and this is an exponential term, you're just going to get fewer and fewer atoms in these higher energy states for the temperature of the sun. A related question might be, calculate the ratio of the number of hydrogen atoms in the first excited state to the total number of neutral hydrogen atoms for the sun. This is actually what we need for the line strength equation. Like we just saw, almost all of the hydrogen atoms are going to be in the ground state for the sun. So we can approximate that the number of neutral hydrogen atoms, which is really the sum over all the excitation states, so that'd be the number in the ground state plus the first excited state plus ... you can really just throw out all of those higher terms and just replace it with a number in the ground state for the sun. Like you can't do this approximation when you go to hotter stars, but for the sun this works. So for the sun, we can write that the number that are in the n equals 2 state compared to the total number of atoms that are neutral is approximately equal just to n2 over n1, which we saw was 5.1 times 10 to the negative ninth. So we get the same answer as we did before, but again, you have to be a little bit careful. If you go to hotter stars, you can't make this approximation, and you have to keep more terms in this series. So let's plot the ratio of the number of hydrogen atoms in the first excited state to the ground state as a function of temperature. Again, we can use Boltzmann distribution. You get that expression. We do this calculation, but now what we're going to do is leave t as just a variable. Right? So we're just going to leave t as t. So you get this, you get minus 118,000 over the temperature in Kelvin. So the number that are in the first excited state to the ground state is 4 times e to the negative 118,000 over the temperature in Kelvin. So if you plot this, we're plotting this from 0 to 15,000 degrees Kelvin. 1,000 Kelvin, this is a very, very, very tiny number. As the temperature increases, this ratio goes up. But even by 10,000 degrees Kelvin, you're still pretty small. You're still less than 0.0001 for this ratio. So you've got to get pretty hot indeed in order to see a significant number of hydrogen atoms in that n equals 2 state. In fact, if you plot it out to 100,000 Kelvin, we see that we're finally reaching equal numbers of atoms in the first excited state to ground state at a temperature of around 85,000 Kelvin. So you have a homework problem. Calculate the temperature where the number of hydrogen atoms in the first excited state equals 1% of the number in the ground state. So you can get some general ballpark idea what the answer should be from this previous plot. That'd be 10% right here. So to have 10% in that upper state, that looks like that's going to be roughly around a little less than 30,000 Kelvin. So, it's definitely going to be less than 20,000 Kelvin, but it's going to be greater than 15,000 because that's 0.1%. So, I would guess that your answer should be roughly 20,000 Kelvin in there someplace just by looking at that diagram. But you'll find out the real answer when you solve it mathematically. Let's look at this next term. So the next term is the ionization state. This is the equation. So this is the Saha equation. So this tells you how many atoms you have in the next higher ionization state compared to the ionization state that you're currently in. In I is the number of atoms in ionization state I. In I plus 1 is the number in the next higher ionization state. You get the partition function. We'll define the partition function on the next slide, but that is a function of which ionization state you're in. So Ne is the number density of free electrons. That is the number per unit volume in the star's atmosphere. Me is the mass of the electron right there. And sometimes it's easier to quote what the number density of free electrons is. More often, people specify what the electron pressure is. So if you imagine a gas of free electrons, what the pressure of that gas would be, and that's just given by the ideal gas law. So pressure is nKT. So if you're given the electron pressure, you can calculate the number density just from the ideal gas law. Chi here is the ionization potential to go from ionization state I to I+1. T is temperature, K is the Boltzmann constant, and there you go. Okay, the partition function. The partition function, Z, don't get that confused with the charge of the nucleus that we're using in the Bohr model. It's a different Z. The partition function is a weighted average of the statistical weights, i.e. degeneracies, of all the energy levels where the weighting factor equals the Boltzmann factor. So the summation is over all of the energy levels for a given ionization state. Gi, remember that's the statistical weight that we defined for the hydrogen atom before. And this term right here, that's the Boltzmann factor. So that's the difference in E to the minus difference in energies over KT. And now we sum up this for all of the energy levels for a given ionization state. So it seems a little intimidating, but we're going to write it out like this. So when J is equal to 1, when we're in the ground state, you get E1 minus E1, that's just 0. E to the 0 is just 1. So that first term in the summation is just the statistical weight of the ground state. Then you add to it the statistical weight of the first excited state times E times that Boltzmann term. And then the third, G3 would be for the second excited state, and so on. In a lot of cases, we can make the approximation that this second term, this exponential term here, is going to be much, much, much smaller than 1. So all of these other terms are going to be tiny compared to that first term. That assumption breaks down in like the hottest of stars, but it works fine for the sun and even for moderately hot stars. So we're going to do that. We're going to assume that all of these terms are negligible, and we're going to write that the partition function is just equal to the statistical weight of the ground state. So this is a much simpler expression than having to deal with this. Finally, ionization potential, we've talked about this before, so we'll need this when you're evaluating the Saha equation. Let's do an example. Calculate the ratio of the number of ionized hydrogen atoms to the number of neutral hydrogen atoms for the sun. So how much of the sun's hydrogen is ionized, how much is neutral? That's what we want to find out. And so this is the Saha equation, and again, we might need that ideal gas law for the free electrons. So we just need to identify all the terms. N sub I plus 1, that's going to be N2, that's the number of ionized hydrogen atoms. Remember the Roman numeral 2 means singly ionized state. Ni is going to be the number of neutral hydrogen atoms. The partition function now, for ionized hydrogen, all we have is a free proton. And the free proton is just a free proton. So there's only one quantum state, and that's the proton itself. And so the partition function, Z2, is just going to be 1. So we can just plug in 1 for that. That's easy. The partition function for neutral hydrogen, we just talked about. We're going to assume that it's just equal to the statistical weight of the ground state, which is 2. For the sun, we know that the pressure of free electrons is about 1.5 newtons per meter squared. That's a average value. So from that, we could actually calculate what the number density of free electrons is from the ideal gas law. These are the constants: mass electron, the ionization potential for hydrogen, 13.6, and the temperature. So take all that stuff, throw it into the Saha equation, and get an answer. So what we find is that the number of ionized hydrogen atoms to the number of neutral hydrogen atoms is 0.00075. So a very, very small fraction of hydrogen atoms are actually ionized in the sun. So now let's calculate the ratio of the number of hydrogen atoms to the total number of hydrogen atoms. That means neutral plus ionized for the sun. Well, you could probably guess we're going to get the same answer as we did before. So to be clear, we want the number of ionized hydrogen to the total amount of hydrogen, and the total amount is the neutrals plus ionized. We're going to divide this equation through by the number of neutral hydrogen atoms. So if you do that, you divide the top and bottom by NH1. So we have NH2 over NH1. The NH1 over NH1 just cancels to 1. And then we have NH2 over NH1. The reason that we do that is that NH2 over NH1, NH2 over NH1, that's what we just calculated from the Saha equation. So you can substitute the result of the Saha equation in for this and for that. And we found that it was, again, 0.000075. So the answer is 0.000075 over 1.000075, which is about 0.000075. So we get the same answer as just what NH2 over NH1 is, and that's just because that ratio of ionized to neutrals is just so much smaller than 1. Now, if we want, we can write this ratio as a temperature-dependent function. So if we go back and plug in the temperature dependence into the Saha equation and just leave t as a variable, we get this result. And that's going to be handy for the next example. So here we're evaluating that now temperature-dependent ratio. And so we're plotting the ratio of the number of ionized hydrogen atoms to the total number of hydrogen atoms from 0 to 20,000 degrees. And so what we see is that if the temperature is much less than, about 7,000 Kelvin, down here, almost all of the hydrogen is neutral. Above about 12,000 degrees, almost all of the hydrogen is actually ionized. So there's a transition zone between about 7,000 K and 12,000 K where the hydrogen is now becoming more and more and more ionized. So there's a phase transition between being neutral and ionized. When that ratio is equal to 1/2, that occurs at about 9,600 Kelvin, or rounding it off, about 10,000 Kelvin. That's a good number to keep in the back of your mind. Of course, when we were talking about calculating line strengths, we don't actually care about the number of ionized hydrogen. What we want is the number of neutral hydrogen. So this is now the number of neutral hydrogen to the total. And so now we find that for less than 7,000, almost all of it is neutral. Over 12,000, it's almost all ionized. Remember that in order to see the Balmer lines, the hydrogen needs to be neutral. So basically, in order to get neutral hydrogen, the temperature of the star has got to be not crazy high. If it's too crazy high, all the hydrogen is going to be ionized and there's not going to be any Balmer lines. So it's got to be down here someplace in order to get the Balmer lines. So to find the total line strength, we can piece together the results that we've gotten so far. So we want to multiply our excitation term by the Saha term. And in order to make this approximation valid over a range of temperatures, we're going to do the following. So we're going to write that the number of neutral hydrogen atoms is the number in the ground state plus the number in the first excited state plus third and so on. We're going to keep the first two terms in that series and ignore all the higher order terms. So we're going to say that NH1 is approximately just the number in the ground state plus the number in the first excited state. So therefore, the number in the second excited state to the total number of neutrals is number in the n equals 2 state divided by the number in the ground state plus the first excited state. We can divide through by the number in the n equals 1 state and the ground state. This term goes to 1. We did this before with the Saha equation. And so you get this expression right here. So the point of doing that is that each of this term here and this term here is given by the Boltzmann equation. We did something very similar for the ionization state. So the number of neutral hydrogen to the total number of hydrogen we saw was equal to this. And again, that term in the bottom was given by the Saha equation. So what we want to do is plug this in for that first excitation term, plug this in for that Saha term right there. So when we do that, we find this, that the line strength should be proportional to this times this function right there. So this is best done using some kind of mathematical plotting program. The results that I've been showing you so far have all been done in Maple. All right, so here we go. The red curve is the one that we've already seen for the Saha equation. So this is the number of neutral hydrogen atoms to the total amount of hydrogen. We saw that it's it's very much neutral for temperatures less than around 7,000 Kelvin. If you get above 12,000, it's almost all ionized. So we want this curve. So when this curve goes up, the strength of the Balmer lines should go up. But the blue curve shows the population of that n equals 2 state in hydrogen. So we've got to have those hydrogen atoms in the n equals 2 state in order to see the Balmer lines. So when this curve goes up, the strength of the Balmer lines goes up. So you can see what's happening. There's a competition between two different effects. If the star gets too hot, everything becomes ionized and you don't see the Balmer lines, but you're getting higher populations in the n equals 2 state of those hydrogen atoms that are still left over. On the other hand, if the star gets too cold, almost all of the hydrogen atoms are in the ground state, and they're not going to be in the first excited state. So you're not going to see the Balmer lines. So when you multiply these two functions, there's like a little region like right in here where you get the strongest hydrogen lines. And when you multiply those two functions together, this is what you get. So again, this curve peaks at around 10,000 degrees. If the stellar atmosphere is too cold, all the atoms are in the ground state and you're not going to get Balmer lines. If it's too hot, all the hydrogen gas is going to be ionized and you're not going to get Balmer lines. So it's got to be just the right temperature to see the lines. Notice that the vertical axis here is times 10 to the negative sixth, right? So we're talking about 1 part in a million of atoms of hydrogen atoms in the sun that are going to be in the right ionization and excitation states to produce Balmer lines. But again, there's a crazy number of hydrogen atoms in the sun as a whole. So even though this number is small, it's still enough to produce, it's still enough to actually see the lines. So you can carry this calculation out for whatever element you want. It turns out that it's particularly simple for hydrogen-like atoms where you can apply the Bohr model of the atom. If you have more complicated atoms, you need a fully quantum mechanical calculation, and that gets a bit more tricky. But people have, of course, done it. And what we can see is that every element in a different ionization states have their own region where their lines are strongest. So we see that the hydrogen lines peak roughly around 10,000 degrees. By the way, this horizontal axis is plotting temperature, and it's on a backward scale. The reason is that for that, as we'll see later. But so the coolest stars, 3,000 over on the right, the hottest stars over on the left. Here's ionized calcium. So ionized calcium has a lower ionization potential, and so that shifts the peak of where you see its lines to cooler stars. So it peaks at around between 4,000 and 5,000 Kelvin. Neutral helium has a higher ionization potential, so that shifts it to higher temperature stars. There's iron, neutral calcium. Titanium oxide is a molecule that's present in a lot of stars. In any case, this is a very powerful technique to very accurately measure the temperature and abundances of different elements in stars by looking at the relative strengths of their spectral lines. And we'll talk about that more in upcoming lectures. In the next lecture, we'll talk about radiative transfer.